Good morning and welcome to this next lecture on vibrations of plates and shells. In the last class we looked at the Rayleigh Ritz method applied to annular plates. So today I want to show you some calculations, okay, or some results related to that. So one thing is, suppose in the way the paper, I mentioned a paper in journal paper from a journal with Professor R.B. Bhatt as one of the authors. Suppose in the way the paper formulates its functions, admissible functions, suppose we say that we take up this phi 1 r a 1 cos 0 theta axisymmetric, okay, plus phi 1 r the same radial a 2 cos 1 theta, okay, one diametral node line, plus phi 1 r again a 3 cos 2 theta, plus now phi 2 r the higher level function in the radial direction a 4 again cos 0 theta, so axisymmetric, plus phi 2 of r a 5 cos 1 theta, plus phi 2 of r a 6 cos 2 theta, plus the next level in the radial direction a 7 cos 0 theta, plus phi 3 of r a 8 cos 1 theta, plus phi 3 of r a 9 cos 2 theta. So this bracket and that bracket, they are the same, okay. So this is same, this is square. If we took this as these sum of admissible functions and we went ahead, used it in the Vm and psi m and differentiated with respect to ai, okay, and found the results, they would look somewhat like this. There is a table n, okay, 0 1 2. So this is diametrical nodal lines. That means this, n1 means this, n2 means this and this, okay. And here we have n going from 0, I mean this number going from 0 1 2 and 3, okay. These are nodal circles. I am showing you the table that is listed in the paper, okay. So now this whole line is axisymmetric line, this entire line is axisymmetric, okay, n0 is axisymmetric, okay. So this first for this set the first value I got is 10.226. Okay. So I will show you the radial function. Okay. At this value of the natural frequency, if I compute the eigenvector, that is A1 through A9, if I compute A1 through A9, that is the eigenvector, okay, and if I add up the phi's, corresponding phi's, then I will get the shape in the radial direction. So I will show you the shape. Okay. Then for one diametrical nodal line I got 21.286. Okay. Then for this, where I had 1 0 crossing, okay, I got 40.207, and for 2 0 crossings I got 97.233, which is way higher than the actual value. Okay. So what I will do now is just show you some of these calculations in Maple, so that you can believe that these are actually doable. So I am shifting to another computer here. Now you have seen the annular axisymmetric resonances. So let me run this code for the annular circular plate. So if I run it, okay. Now let us see here. So I have coded all the relevant terms, so it will be easy. So this represents the eigenvalue and eigenvector matrix, okay, and the eigenvalue at this point is 996, which we will see in the non-dimensional terms what it is, okay. And the corresponding eigenvector is this. So first 3 terms relate to phi 1, next 3 relate to phi 2, and then the last 3 to phi 3. Okay. So what we have, -1 for phi 1, 0.0529 for phi 2, and -0033 for phi 3. Okay. So if we do that over here, so here this line is relevant to that. So -1 phi 1 plus 0.052 phi 2 minus 0.0033 phi 3. So if I run it, okay, so you can see that I get 10.22 as a non-dimensional frequency, and this is the hole is below this, okay. It's a small hole. So the plate begins over here, annular plate begins over here, and it ends at the outer edge, okay. So there is no node point. So this is the shape in an axisymmetric manner. So you can rotate it about this vertical axis, that is the shape of the plate, okay. So that is the very first axisymmetric mode with 10.22 as the non-dimensional resonance frequency. Now next I will show you for a frequency value of 15,407. The corresponding eigenvector is here. So phi 1 is minus 05283, phi 2 is -1, and phi 3 is minus 0.035. Okay. So if we look at that set of numbers over here, okay, so so you should remember that we had 40.207 in the first column. Then this is the annular plate again. So the hole is below this value, and there is a node, and it finally reaches the edge. So, if we now rotate this shape about this vertical axis, it is an axisymmetric mode. Now, this will be a circular node line, okay, this circular node line. Okay. Now, lastly, we look at 90,104, the corresponding eigenvector is minus 0.00525 for phi 1, minus 0.0354 for phi 2 and 1 for phi 3. So, if we do that calculation here, this is what we get. So, the non-dimensional number is 97.233. I told you it is very high, okay. It should be around 80, but I have taken only till phi 3. So, the result will be inaccurate and over computed, okay. So, again if you see the hole is below this value over here, that is the annular plate, and then it has 2 zero crossings and it reaches the edge. So, if this shape is now rotated about the vertical axis, that is a axisymmetric mode with 2 nodal circles, okay. So, that is for the annular plate using Bhatt polynomials, okay. Now, the next set of calculations are here. These are for the rectangular plates, okay. So, let me uncomment the first one. So, this is for a clamped plate, and if I zoom it, okay. So, this is for a this is the shape for a clamped plate. So, if I now run it, okay. So, now if I go to this point here, as I said, I have already programmed it, okay. So, if I comment this and comment this, here we have clamped. So, there is one term, two term, and okay. So, let us do the simplest term first. So, let me comment this here and do the simple term. So, if I run it, okay. So, now you can see this is the very first mode of a clamped plate, okay. The displacement is 0 at the edges and the slope is also 0 at the edges, okay. Now, let me go and take a higher mode. This is a higher mode, okay. It is like a 1-2 mode. There is a 2 half cycles in this direction 1/2 cycle. Okay. Again 0 displacement at the walls and 0 slope at the walls. Then let us do one more higher order mode. So, you can see there are now 3 half cycles in this direction, okay, and 1 half cycle. It is like the 3-1 mode, again same set of boundary conditions. Okay. Next what I will do, go up and I will run the clamped and free case. Okay. So let us now take the clamped free. I will comment this one. Okay. So, this is a clamped free case. Okay. So, these two edges are clamped, these two edges are free, and I am showing a very high order mode in this direction, okay, and there is a low order in this direction. So, remember this, I will show a very low order mode to begin with again. So, that ends here. So, this would be a low order mode. So, let me comment it. Okay, if we run this, okay, so that is a low order mode. Okay. So, you have displacement and clamping condition at these two edges. Let me show you an intermediate mode. So, so let us see this, yeah. So, comment. So, if I run this, so you can see this is an intermediate mode. Okay. Along this line there is no node, along this line there is one node, whereas the first one had two nodes along this line. Okay. So, that is a clamped free. Okay. Lastly, I will show you simply supported. Okay, so let us do a simply supported. So, let us run it. So, I will close this, open this, let me block, okay, yeah, let me block this, let me put a colon here. Okay, so let us evaluate. Yeah, so this is a simply supported mode. So, it is simply supported on 4 edges. This is 2 half cycles in this direction, 1 half cycle in this direction. So, let me change it. Let me take a very simple one. Let me put a comment first. Okay. Okay. Now, this is the first mode. Okay. So, let us continue with the remaining part of the lecture. Okay. Further, you could do the Rayleigh Ritz on a cylinder. Okay. So, from the general set of equations, if you plugged in say A1 is equal to 1, A2 is equal to A, okay, R1 equal to infinity and R2 equal to A, then you will get the cylindrical set of equations. Okay. Now, if you form the V max, okay, alpha 1, alpha 2, alpha 3, E over twice 1 minus mu square epsilon 1 1 square plus epsilon 2 2 square plus twice mu epsilon 1 1 epsilon 2 2 plus g by 2 epsilon 1 2 square a1 a2 d alpha 1 d alpha 2 d alpha 3. Okay. Then you form your K max, kinetic energy max, as omega square rho h by 2 integral alpha 1 integral alpha 2 u1 square plus u2 square plus u3 square a1 a2 d alpha 1 d alpha 2. Okay. And from here you form your Rayleigh quotient. Okay. Then you choose your admissible functions, choose admissible functions. How do you choose them? You have three directions. Okay. You have three directions. So you choose as a1 cos m pi x by L cos 0 theta plus a2 cos m pi x by L cos 1 theta plus a3 cos m pi x by L cos 2 theta. Okay. Okay, let me do one thing. We are running out of time, so I'll continue in the next class.